Thank you. Hi, I'm Paula, and I'm a PhD student at Queen Mary University of London, and today I'm going to be telling you an application that GPR, or Gaussian process regression, has in radio cosmology. So in cosmology, we're very interested in mapping out the large-scale structure of the universe, so where matter is located on a large scale in our universe, and this helps us learn more about our cosmological model, things like modified gravity as well, so we really want to observe it. But most of the matter is dark, so one of the things we can do is try and map the matter using hydrogen, because after reionization, most of the neutral hydrogen, or H1, in the universe can be found inside of galaxies. So we can simply point our telescopes at the sky and try and detect a 21 centimeter emission of galaxy, and where there's more intensity, that means there's more matter present. Where there's less intensity, that means there's less matter present. This is a great way to map large areas of the sky very quickly, but we end up also detecting really huge foregrounds that we need to get rid of. And the idea behind this project was that GPR has already been used for foreground removal in high redshift studies of epoch of reionization, but we wanted to see if it would work for low redshift studies of the large-scale structure. And so we wanted to ask how would it work in our case, how does it compare to other methods such as PCA, and could we use it, for example, for the SKA? So we start by assuming that our data, which are SK-like simulations, and each of its components, so the foreground, the H1, and the noise, can be described as a Gaussian process. And in essence, what this means is just that you can describe each of these signals using a different covariance function. And the covariance function tells you how your signal behaves as a function of whatever variable it's a function of. So in our case, it's frequency. So the smooth foregrounds are very smooth in frequency, and they're very bright. So their covariance function is going to reflect that. But the 20 centimeter emission is not smooth in frequency because it's tracing the structure of matter, and it's very faint. So it's going to have a very different covariance function. And essentially, to do the foreground removal, we just take these different covariance functions in our data, and we use it to predict what the foreground looks like in our case. And we find that we can indeed do this. So we're trying to recover the true H1 power spectrum, and which is the black solid line. And we find that GPR, which is the green line, can indeed recover the small scales really well, better than PCA. But on large scales, it performs pretty much the same as PCA. But then when we decompose into the radial and transverse components, we find that GPR performs really well in the radial direction, which makes sense because we're mostly taking into account radial information, and a bit less well in the transverse direction, but still similar to PCA. Thank you. So just to conclude, we find that it is indeed possible to use GPR as a foreground removal in low redshift H1 intensity mapping studies. It performs better than PCA on small scales when you're only looking at smooth foregrounds, and it also performs better in the radial direction and in the transverse direction. And one thing about PCA that's important is that you have to choose a number of components to remove in order to remove the foregrounds, and you can't really train this using the data in any way, but you can do this with GPR by simply finding the best fitting covariance function. So this is another advantage it has. And we release some user-friendly, publicly available code. If you're interested in doing this yourself, it has a lot of introductory notebooks. So if you're interested, check that out. Thank you very much.
Thanks for that.